We talk about the cosmological perturbations with the general relative theory. In the previous video, we already talked about the cosmological perturbations in the Newtonian approaches. This Newtonian theory can be applied to the non-relativistic and the subhorizon scale. And we talk about the three cases: no gravity and no expansion. And we ask the gravity and expansion slightest. And we can bounce that there is a Jensen instability, which is the density perturbations that grow exponentially. And we applied this Newtonian perturbation to the matter cases, especially the cold dark matter. We can evaluate the going both through the density perturbation during the radiation and the matter dominant era. So continuing the previous video, today I want to talk about the cosmological perturbations with the GR, the general relativity theory of Einstein. So in the Newtonian approaches, we just perturb the energy density and the gravitational potential. But now we should generalize this perturbation to the tensor version, because GR is written by the space-time tensors and the stress energy tensor. So now the gravitational potential is replaced by the matrix G mu nu, and the energy density law and the pressures will be replaced to the stress energy tensor T mu nu. So first of all, let's talk about the matrix perturbation. The matrix is given by the G mu nu, which contains the information of the space-time. And we can perturb around the blood apparel double matrix G bar mu nu. So the small perturbation is given by the delta G mu nu. Then we can generally write the matrix perturbation for only the linear order in the following form. Here's the eta is the complement time. So the scale factors are multiplied in front of the eta scale, and we only take the linear order for the complement time and the cross term of the complement time and the spatial part and spatial part. But we can rearrange these linear perturbations with the decomposition into the scalar, Back-Tensor, and tensor part. This process is called the SVT decomposition. So for example, the cross term Bi can be decomposed to the divergence loss, Back-Tensor, and the scalar. And the tensor, the Hij, can be decomposed to the scalar part and the divergence loss, Back-Tensor, and the divergence loss and the trace loss tensor. Although this divergence loss can interpret as a transverse. So now that there is the three modes of the matrix perturbation. Here's the A, B, C, E, which is included in the scalar mode, and here's divergence loss, Back-Tensor, Bi, and Ei. It's classified in the vector mode, and the transverse and trace loss tensor mode. We can count the degree numbers of the freedom. So in the scalar mode there are 4 scalar. In the vector mode there are 4 degrees of freedom, because this Bi and the Ei only carries the spatial part. So originally it has a 3 free parameter, but by the transverse or divergence loss condition, the degree of freedoms are reduced. So each Bi and Ei mode contains the 2 free parameter. Similarly, for tensor mode in the EIJ, originally it has a 6-degree freedom because it is a symmetric one and only considers a spatial part. So the 3 times 2 divided by 2 gives a 6 free parameter. But the twice last condition reduces the 1 parameters, and the divergence loss or transverse condition gives us 3 constraints. So the 6 minus 3 minus 1 gives us 2 free parameters for the tensor mode. So if we sum up this all the free parameters for each scalar vectors and tensor modes, then there are 10 independent degree of freedoms in the metric perturbation, and this is consistent with the symmetric condition for the metric tensor. Because there are, for the twice parts, there are 4 free parameters, and for the twice free part, there are 6 parameters in here. So now we got the estimated decompositions of the metric perturbation, but the some metric perturbations is not physical quantity, because in the general relativity theory there is a diffeomorphism, which is a coordinate transformation, and there are some gauge of freedom or gauge choices that remain. So some perturbation variables does not show that the physical quantity, but that they are some coordinate artifacts. So we can reduce the some metric perturbation by choosing the specific gauges. We can consider the following infinitesimal coordinate transformation for the space-time x mu to the x mu tilde. This Cauchy mu can be decomposed to also the scalar and the vector part again, for the temporal parts and the spatial parts. And for the spatial part, there is scalar and the vector decomposition, and these vectors satisfy the divergence loss conditions again. So to find the transformations of the metric under the following coordinate transformation, we can use the transformation rule of the tensor. So G mu transform to the G tilde alpha betas with the coordinate transformation factors. For example, for the 0, component, we can compute the transformation rule from the G00 to the other tilde form, but the other G0I or Gij tilde has the some quadratic term, so that this term can be ignored. So the G00 and the G00 tilde can be transformed like that. And we can expand this G00 tilde with the tilde coordinate and expand this to this scale factors and the perturbations in the tilde coordinate by using the Taylor expansion and also the taking the both again. And we can obtain the matrix in the tilde coordinates in terms of the until this coordinate. So by using that, we can obtain the multiplication, the transformation rule for the metric perturbation. We can compare the right hand side and the left hand side. Then for example, the metric perturbation A transforms under the coordinate changes like that. So this additional term T and L comes from the coordinate transformation, and the curly hubbles mean that the A primes of the I, whereas the prime mean that the derivatives for the component time. So similarly, we can obtain the transformations of the other metric perturbation under the coordinate changes. For example, this is for the scalar mode and the vector mode and the tensor mode. And we know that there are two scalar mode and one divergence last factors for the gauge choices. So we can remove the two scalar and one transverse factors. So as a common choice of the matrix perturbation, we can impose the two scalar mode B and E set to be 0, and EI, this factor mode also set to be 0. Then in this gauge choices, also called the Newtonian gauge, why this term is called a Newtonian? Because this is similar to the Newtonian approaches. So the matrix perturbation can be simplified to the following form. So now the B and the E scalar modes are died, and also the EIs are died. And usually the scalar mode and the A and C are denoted by the psi and the pi. And our interest is focused on the scalar perturbations because the vector mode will be died during the cosmological history, and the tensor modes keep the gravitational wave. But this is very weak in the CMB observation. But the scalar perturbations influence the very large perturbations over the cosmic history, and especially for the torsionless, torsion-free material, the psi and the pi are the same, so that we can only denote this as just one parameters, just capital pi, and this corresponds to the gravitational potentials in the Newtonian approaches. So we finished now the matrix perturbation, but in the general relativity theory there's also the energy stress tensors in the right hand side. Similar to the matrix perturbation, we can perturb the energy momentum stress tensor through in the linear order. The general orders contains the backgrounds, energy densities, and the projects, and we can take the linear order with the delta rho, delta p, and the velocity. Again, the velocity can be decomposed as the scalar velocity and the transverse velocity. And there's anisotropic stress as the orthogonal term of the stress tensor. But usually this anisotropic stress will start to be 0. Similarly, under the gauge transformation or coordinate transformation, this matrix perturbations changes. And also we can choose some specific gauges. So now that we can generalize the conservation equation. In the general relativity theory, the conservation equations are given by the covariant derivatives of the energy momentum stress tensor. And for convenience, we will define the momentum density, which is 0I components of the energy stress tensor. And for the continuity equation, we can obtain this with the nu equal to the 0. And we can expand this, the covariant derivatives, with the Christopher symbol. And the Christopher symbol, inside of the Christopher symbol, the matrix perturbation will be contained, because Christopher symbols are defined by the both derivatives and its linear combinations of the matrix. And only taking the birth order, then one can obtain the continuity equations in the following form. So now the changed part is the first of all this one. Now the epochs of the scalar perturbations are this. So the time dependence of the matrix changes the density perturbation. And if we take the momentum that is extremely smaller than the density, then the Newtonian limit can be recovered. So the delta P and the P bar all died, and the Newtonian approaches reproduces again with the Hubble terms and the expansions impact. Similarly, by taking the component index nu as I, then the conservation equation yield the Euler equation for the momentum conservation. And similarly, if we take the project extremely smaller than the energy density, then we can obtain the Newtonian versions of the Euler equation. So in the final step, we can generalize the Poisson equation of the Newtonian gravity to the Einstein equation of the general relativity theory. And similarly, we can take just the linear order. The Einstein field equation is given by the g mu equal to the 8 pi g times the t mu. For each component, 0, 0 component and 0, I component, the twice pass through the ij and the last through the spatial part, we can obtain the each equations in terms of the metric perturbation, especially the scalar perturbation pi and psi, and the metric perturbation delta rho, delta p, v, vi, and momentum density qi, and anisotropic stress capital pi ij. So for the 0, 0 component, this is relativity versions of the Poisson equation. So this is the original Poisson equation, but now the scalar perturbation contributions are added. And the 0, I component, this is momentum constraint. Here's the momentum densities added, and in the left-hand side, similarly the scalar perturbations contributions are added. And for the thrust pass through the ij, this corresponds to the project equation. On the right-hand side, there is the project perturbation, and also the scalar perturbation impacts are added. And the thrust last pass through the ij component corresponds to the anisotropic thrust, capital pi ij. Also, there are scalar perturbation in the right-hand side. But we'll consider the anisotropic thrust balances. So this is equal to 0, so we can find that the capital pi and the capital psi are the same. So we talk about the general relativity versions of the cosmological perturbation with the metric perturbation and the matter perturbation. And the metric perturbation can relate with the scalar vector tensor decomposition, and especially that there are gauge rhythms by the coordinate transformation, so that we can remove some perturbations, and especially we will focus on the scalar perturbation, capital pi and capital psi. And after the boundary matter perturbation, we obtain the conservation equation in terms of the density, project velocity, and anisotropic thrust. And combining this metric perturbation and the matter perturbation, we obtain the linearized versions of the Einstein equation for this component. These frameworks are generalizations of the Newtonian approaches, and this can apply to the superposition mode and the relativistic mode for the cosmological perturbation. In the next video, I will solve this equation under some simplifying condition, like some adiabatic perturbation, or perplexed fluid, or some specific cosmological error, or superposition mode, and also some applied to the specific example, like the radar matter perturbations and the radiation perturbation, and this will give us some observational result, like some matter power spectrum or cosmic microwave background.